tell you when we're live. No. Wait.
You have been lied to your whole life. You are not made of matter.
It's time to wake up, universe. Okay, how are you all doing? And welcome to Wake Up Universe. Today's topic, we're going to be talking about none other than Einstein's famous theory of general relativity.
E equals mc squared.
So let's write that out, shall we?
Mm-hmm.
Energy is equal to energy, E, represented by E, is equal to mass m times c squared, the speed of light in a vacuum.
Mm-hmm.
So let's just talk about this famous equation here. What does it mean? What does energy equals mc squared mean? Well,
we've heard all about it, I mean, everyone knows Einstein said E equals mc squared. We all know that. And we all know that he was a smart guy, but, we don't really understand what it actually means. So that's what we're going to investigate today.
I mean, the fun thing is that not even he understood what it means. But here's the thing to think about. Okay, the general idea behind it. Energy is equal to mass times the speed of light in a vacuum. Now, what that means is that energy is just mass moving at the speed of light in a vacuum. Energy is mass, which also exemplifies something called the de Broglie principle, meaning that any particle has and will continue to retain a wave of itself. The larger this object is, or mass in general, the more mass something has, the smaller its energy wave. So, essentially, well, forget the law of conservation of matter, forget the law of conservation of energy, because they're both kind of a lie in some way, because you can turn energy into matter, and matter into energy. But to have energy be matter, you need to have a lot of it. To make matter out of energy, you have to have lots and lots of energy to create said matter. Now, it's really odd to think about that, because doesn't that mean that the law of conservation of matter and the law of conservation of energy are a lie? Doesn't that mean that energy isn't conserved? Because you can turn energy into matter, and that therefore means there's less energy in the universe, doesn't it?
I was taught in all my science classes, they always taught me, Sebastian, law of conservation of energy and law of conservation of mass. Mass will never, ever deteriorate. Mass, it gets transferred through the chemical equation. And now, I'm even actually right now learning about this in my chemistry class. And crap, it's not true.
I mean, It's really weird to think about because in a way it is true, but and it's very hard to do this. It doesn't happen very much. But yeah, let's look at a chemical equation, shall we? You know. Let's just take.
Let's see.
Something you can burn. Well, photosynthesis, like a combustion reaction.
Oh, combustion. Okay, let's see. Oxygen with.
Well, let's just take hydrogen and oxygen for example.
Mm-hmm.
So you have hydrogen, H2. It's something called a diatomic, which means it always likes to stick together. 2 atoms of hydrogen plus 2 atoms of oxygen.
Same thing there.
Leads to 2H2O. Now we're gonna need 2 oxygens, right? But this means 4 hydrogens. That is an issue, but we'll talk more about balancing equations in another episode. So what we're going to need is we're going to need 2H2 because we need to have 4 hydrogen as exemplified here and 2 oxygen. The 2 also applies to the O. But anyways, what this means, this is a general, this is the combustion of water. Actually, this isn't a good example. Let's think of a combustion reaction. Let's see. Propane, for example, is C3H8. Yep.
Oh, yeah.
So, this is propane, C3H8, and what we're going to do is we're going to add oxygen to it. The reaction transmits to CO2 plus H2O, because any combustion reaction, which is the same thing as burning, any burning reaction, which is a chemical reaction, you are oxidizing, you are adding oxygen to said thing. So we're burning propane, right? We're going to need, this is an exothermic reaction, so we'll put plus heat down here, which we'll talk about again in another episode. So we have to balance this, but again, we won't worry about balancing right now, just for the purpose of our conversation.
Just for the idea.
The idea here is that you're burning propane, but there's a balance of matter. That's the idea. That's the whole idea behind balancing. Because there should be the same number. There should be 3 carbons over here, which is why we're going to call this 3CO2, because we need to have the same number of reactants and products. So if there's 3 carbons over here, then there needs to be 3 carbons over here. If there's 8 hydrogens, there needs to be 8 hydrogens over here, which means we need to add 4 there. So we also need to have the same number of oxygens, and obviously there's 6 oxygens, 3 times 2, because we have 2 in this, so 6 plus 4. 6 plus 4 is 10, which means we need to have 10 O2 here. So there's 3 C's, right? There's 10 oxygens, as we verified, and there's 8 hydrogens. So this here is a balanced chemical equation. Oh, all right, I'm sorry. This is wrong. It would be 5O2 because you need to have 5 times the 2 oxygen. 5O2. O2 is also a diatomic. So we would have 5O2, which is the same thing as 10 oxygens, and we have 6 here and 4 here, which means we have a balanced chemical equation. Now, this is a lie, because most of the time, this is what happens. Most of the time, you don't have to worry about this changing. So we just assume it to be law.
No matter what, which is not true.
I got it. Matter. No matter what, because matter, law of conservation of matter, right? It states that there will, regardless of any chemical reaction, there will always be the same amount of matter in the universe. So, back to what we're trying to say here. The idea behind this is that, okay, we've been adjusted to this our whole lives. We've seen chemical reactions. We've measured them in a lab. And this always seems to work. Same thing with energy. Let's say you put in an activation energy for an equation. So, for said equation, that same equation we just had up here, C3H8 plus 5O2 converts to, what was it? It was 3CO2 plus 4H2O. And then, because it's an exothermic reaction, it means it gives off heat. There is an added amount of heat that disappears. And again, in a future episode, we can talk more about how to know what amount of heat that is. But in this reaction, what we need to realize, okay, inside of this propane is energy stored within the chemical bonds between the hydrocarbons. Hydrocarbons are carbons and hydrogens bound to each other. There's lots of energy in hydrocarbons, which is why we, burn things. Like coal, for example, it's a hydrocarbon. So what does this mean? There's energy in this bond, and then we add oxygen to it, and it gets given off. So what happens is that this is actually losing energy, so there's less energy within bonds than there was originally. So, again, we should have the same amount of energy stored in these bonds here, in the hydrocarbon bonds, as we should have total within these carbon. There should be the same amount of energy here than there is, as there is in the carbon, or the CO2 and the H2O plus the heat. The heat given off is the stuff that's not stored in these two, but we typically say that the amount of heat given off is most of this. So, again, some of the energy is still stored in those bonds. But as the bonds reform, that's when heat gets given off, which is, again, the whole point of a combustion reaction. So, same amount of energy on both sides, right? Well, again, most of the time, that's the case. And really, with regular chemical reactions, we can always assume that's the case. But again, it's an assumption, which means it could be false. And according to this equation, E equals mc squared, there is a possibility that assumption could be wrong.
Exactly. So you don't want to ever assume, did you just assume the chemical reaction? Don't do that.
You just assumed. And that is what they've been teaching your whole life, because every experiment that has been done in a lab, mostly that is, until just recently, until Einstein brought up this idea, we just assumed that the law of conservation of matter and energy were separate. But what we really need to say is the law of conservation of mattergy. And I know that's not a word.
Not yet.
Not yet, that is. Because no one really wants to explore this area because it just doesn't apply much. But just because it doesn't apply much doesn't mean it doesn't ever apply. Because it did. It did apply way back in the production of our happy little universe. So our happy little universe now was the size of a single singularity. A singularity, we can explain more again when we talk about black holes. But it is extremely small, but very, very dense. It's the idea, it's the thing that produces a black hole. When you have all of this mass being condensed to a very high density, there is a limit to how dense something can be. The maximum density possible in the universe is a singularity. So that is what this guy is here. So inside of this singularity, let's get a bigger picture, shall we? Don't judge my magnifying glass. But inside of this, we have matter, right? Then we have something called antimatter. I'm going to label it with A's. Just as well. There should be the same amount. 1, 2, 3, 4, 5, 6, 7, 8. There should be the same amount of antimatter and matter as there is. Because law of conservation of energy, right? Well, mattergy we're going to go with. Because you conserve mattergy. Or whatever makes up these two things, because they are the same thing. So it should be one law and not two, which is where the laws come in, because they're technically correct when you put them together. So, again, what happens? So you have antimatter, right? You have hydrogen. Let's look at hydrogen, for example. Regular hydrogen has one proton, and going around it, it has an electron. This electron orbits. We're going to label it with an E-, and it orbits. This is a hydrogen atom with one proton serving as the nucleus. Antihydrogen's a little different. You have something called an antiproton, which, believe it or not, has a negative charge. The antiproton has a negative charge, and going around it, we have the positron. The positron orbits, what happens? These two are the exact opposite. What happens when they come in contact with each other? Well, the antiproton cancels out the proton, and the positron cancels out the electron, creating an output of radiation energy.
So two different forms of matter put together will give you energy, if you have enough of it in specific quantities and specific situations.
For every atom of anti-hydrogen, there must be, in existence, according to this theory, an atom of hydrogen and vice versa. So in the creation of this universe, at our singularity, the idea, the Big Bang talks about how at this singularity there was matter, there was antimatter. It came in contact with each other with a huge outburst of radiation and other energy to expand our universe outwards.
But outwards into what?
Outwards, hard to say. Infinity, I guess. And so what happened at this singularity was you had no space between atoms. It was nothing but complete density. But now in our universe, we can refer to something called space. This stuff called empty space, which is literally complete nothingness, something that we don't know how to define. It's not matter, it's not energy, it's just empty space that energy once passed through to keep expanding our universe.
And although one thing that you need to remember is that as the universe is expanding, it is not expanding into space, because space follows the laws of time. Outside of the universe, outside of space, there are no laws of time. Time doesn't exist outside of the universe. So that would be something very interesting to think about. That in reality, this nothingness is even more nothingness than space. As we always say. Oh, and just to point out something I think everyone should know about. Jerber mugs right here, custom made, custom built.
Yeah, it has the lovely Wake Up Universe logo on it, found at shop.spreadshirt.com, and I customize it to put my name on here, Jer Bear, plus the bear on the back.
This is a bear. And right here, Sebastian. So, if you send us your...
So, actually, another thing, we'll get to this at the end, we'll see what happens to the Wheel of Technicality, but wherever, if it happens to land on WinFace, we will select someone to win a free Jer Bear mug. So what I'm going to ask you to do is if you send us a clip of yourself saying, "Hi, this is my name, and I'm from here," so a city and a state, "I'm from here, and this is my WinFace," and hold a pose of yourself, which is good. Hold a pose of yourself, saying, "This is my WinFace," and then you're going to say, "And now it's time to spin the Wheel of Technicality." And so then we'll put that in our videos, and we will have that right before we spin the wheel.
And you will be famous.
And you will be known to all that watch my videos. And just as well, send that to the Jer Bear fan mail, which is going to be in the description of this video a little bit later. It is jerrrbear333@gmail.com. If you submit to that, what happens is when the wheel lands on WinFace, which does happen sometimes, then we will pick the first person or the latest person, the last person who sent a video, the most recent person who sent a video of themselves will win a Jer Bear mug. So, and then we're going to ask you to send us your address in the Jer Bear fan mail account, and we will mail one of these cups to you. It can be your own. So, yeah. But back to energy here. We'll talk more about this, but so if we can convert matter and antimatter into energy, then what does that mean? Doesn't that mean that we can convert matter back into, doesn't that mean we can turn energy into matter too? And so that is really the idea behind what we're saying with the Big Bang here. So the Big Bang. We talked about that, but China actually is working on making a very powerful laser.
China.
It is currently of a status of 5 million billion watts. 5 million billion watts, or 5 petawatts.
Which is a lot.
That's a very high quantity of energy. Now, it's still not powerful enough. I mean, heck, we have no clue how much energy you're required to have. This equation helps us know, but really, we have to figure it out on our own. So, isn't matter then just highly compressed energy? So, are you really made out of matter?
You're not.
You're not. You're made out of energy, or mattergy, if you will.
Metallurgy.
Mattergy. So, mattergy. What about it? What can we know about it? What do we know about it, and what can we do with it? So, that's the whole idea here. Now, again, back to Einstein's theory, if there is matter, then doesn't that mean there's an equal amount of antimatter?
Which means somewhere out there in the universe, there is antimatter. And that antimatter, if it comes in contact with matter, will form energy, radioactive decay, everything.
Radioactive energy. That's bad, right? But of course it has to be the exact. You have to have an antihydrogen come in contact with hydrogen atoms. It has to be the same atoms come in contact with each other. The same molecules come in contact with each other. They cancel each other out.
In the same amount.
We can't just have, let's say this mug was antimatter and we set it on top of this bench here and this bench is matter. It wouldn't just react because this is plastic laminate and this cup is ceramic. So that'd be anti-ceramic, which, well,
hopefully doesn't exist.
I mean, it wouldn't help.
And
the cool thing about this, what does that mean? Forget nuclear reactions. Forget nuclear power plants.
Forget nuclear bombs.
Forget nuclear bombs. So unfortunately, we have something that's going to wipe those out of existence if we find it.
The end of all things.
We're going to have something called antimatter reactions. And they produce a lot more energy, so energy bills are going to go down. But, uh-oh, if Russia decides to start another Cold War...
We're in for it.
Well, if they have possession of those things, that's a big problem. But it's really cool to think about, because it must be out there. According to this equation, according to that equation, it must be out there.
And
because...
Oh, yeah.
For every amount, for all matter, what happens is when energy, let's say we have this powerful laser here. What this does is it puts half of its energy into the, we'll just say antihydrogen, we'll call it antimatter for now. Half of the energy is going to go into antimatter, and half of the energy is going to turn into regular matter. So you're going to have a balance of both. So it always creates a balance. That's the whole idea. Universal balance. So what happens is that all of this energy can be compressed into two forms. You can't create one form without the other because there has to be a balance. There has to be this law of conservation. I'm just going to call it the law of conservation of charges, even though that's not really a law and it's not a thing at all. I'm just calling it that right now. There has to be a balance according to this equation. And that was something that Einstein started to realize, but other people used this equation to figure out the existence of antimatter. So Einstein gave us the equation. We found out more about what it did.
Mm-hmm. And now we know that there is antimatter out there. Somewhere out there.
I mean, there must be. Unless the way people took this is wrong. There has to be a balance because, I mean, how else can we turn matter into energy? The only thing that we know of is things like what? We have, as I mentioned, we have chemical reactions, we have combustion reactions that deal with the bonding of electrons, which are on the outside, right? We have our atom and our electrons. What happens is that electrons are shared in a covalent bond, or an ionic bond. What happens, like NaCl, we have Na plus, for example, NaCl and Cl minus. So sodium is lacking an electron, and chlorine has an extra electron than it should. charged atoms. They come together like a magnet, and they stick together.
Which is how magnets work.
Which is same thing that magnets work. That's an ionic bond. But so either way, they're sharing electrons. What other reactions do we have? We have nuclear reactions, right? We have, let's say this is a neutron, and this is a uranium atom. This is the nucleus, blah, 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 electrons, lots of them going around it. To be more specific, the atomic number of uranium is 92, I believe it is uranium. And what we want is uranium-235, a specific isotope that has 235 minus 92. So 92, the atomic number, is the number of protons. And so we know that it has 3 and 23 minus
23 minus 9, that would get us to
14. Yeah, so 143 neutrons inside of a uranium-235 atom. What we do is, because it's already very unstable, it's giving off radiation, it has so many particles that it can barely hold itself together in the form of an atom. So we shoot a neutron at it, and what this does is it breaks it apart into two atoms, two different atoms, which are no longer uranium, because you have half the protons. So you have half the protons here and half the protons there, and you have a balance of things. Now, eventually, with irradiation, this radiation is given off, makes more plutonium, which is actually a higher atomic number than uranium. This is a nuclear reaction, but yet we still have matter. Some of that matter given off, some of the energy, really, it's the energy that was stored within the bonds in the nucleus. Now, I guess you could say, in some way, some of this matter does and can form energy. But mostly it's about the bonds in the nucleus. That's really what nuclear reactions are about. So what we're talking about is a completely new reaction that you require antimatter for. And that is the antimatter-matter reaction, which makes ourselves energy. Or energy, highly compressed, creating the two forms. Just as well, we have matter creating the two forms. Other than the two forms, we also have, there's just the two forms, I'm sorry. What does this mean? There's a way we could generate lots more energy. There's a way we could do a lot more things with this. But it's highly dangerous. But out of that, we have CERN, right? CERN is in Europe. It's actually the, I can't remember what it stands for, but CERN is in Europe. I believe it's in Geneva. I could be wrong, so don't quote me on that one. But CERN. What is CERN? CERN, actually, one of the things they do at CERN, they have something that creates antihydrogen. They're producing antihydrogen there. Now the problem, they can't hold on to it very long because the antihydrogen comes in contact with hydrogen and boom, poof, and then it's gone. They can't regulate it. What they have to do is they have to have a huge magnet with the stuff, and then it's gone. So it's really hard to regulate, but if we could somehow improve the things that are done at CERN, because we can talk more about how CERN does that in a future episode, but we're more talking about antimatter and matter, just specifically, you can make energy into matter. So, aren't you really just compressed energy? Isn't that what matter is? Well, yeah, that's pretty cool. Which means, though, that there must be an equal amount of matter as there is antimatter somewhere in the universe.
And you don't want to run into it.
So, not good. Anyways, that's that. It's time for today's Cash Craze.
Stock market. Let's talk. Now, as anyone can know, Now it's time to talk about the stock market, my friends.
Okay, let's talk about stocks. So, I don't know if any of you have heard about Trump's lovely
Tariffs.
tariffs, and it's time to talk about the trade war.
Oh, yeah, this is going to be interesting. So Trump actually, he decided in, he was thinking of protecting, steel workers here and aluminum workers. So the idea that he had was to impose a 25% tax on aluminum and steel coming from certain other countries, which is now having a very, very interesting effect on our economy and our stocks.
So, we're going to call this Trump's trade war.
If you're a Trump supporter, watch this. If you're not, watch this.
So, Trump, right? He decided it was a good idea, and to be honest, I really think the United States should be more dependent on these things. But most of our steel, believe it or not, does not come from the United States. It comes from other countries. Foreign trade is what allows us to take this. We have shipments and a tariff. Just to define it, a tariff is a tax on imports from other countries. So, why is this a problem? Other countries are shipping goods to us. We need steel for all kinds of things, right? Mainly construction. Every huge building, every building is built out of steel. Every foundation in New York City, Chicago, every tall building that you have ever seen. Trump Tower, for example, which I kind of find funny, is non-American steel. Most of it, at least. A lot of Chicago, believe it or not, is American steel. Older buildings in Chicago are American steel. In particular, they are Carnegie steel, which we can talk more about Andrew Carnegie in another episode. Andrew Carnegie. So, he's quite a man. What's the problem with tariffs is that everyone needs, lots of different companies need steel. Just as well, they've been cutting, they put a tariff on aluminum. So everything aluminum, all your favorite Huffy bikes, all of your favorite different bikes there are going to be an issue. A lot of construction is going to slow down. We don't have steel. So what is the effect that this is having on the American economy? Everyone is having huge fears of the trade war. Just think about your phones. All of the components in your phones. There's aluminum in your phone. And that's an issue. That's part of, not only is, Apple slowing down because of
this guy's gonna go.
The iPhone X, Apple is slowing down because of Trump's trade war. And it looks like we're having an issue with our whiteboard. You hold that.
But you also need to understand why Trump decided to do this. Now, the idea would be to protect steel workers, American steel workers, so that we can, because they have a lot of competition from overseas. But 25%, my friends, is something crazy. It may help some steel workers, but it's going to destroy our economy if we keep this up for long enough.
Yeah, it's quite an issue. So, what we're going to look at is the graphs and the outcome overall on some major companies. So what we're going to look at is everyone's favorite. So Bitcoin, believe it or not, I don't know whether Bitcoin is affected by this, but the Bitcoin is, wow, they are dropping like mad. They kind of slow, they kind of, boom. And we're seeing lots of slow movement, dip down, back up again, back, and here we are. Bitcoin is kind of at its lowest right now, as they've been in a while. We were up here for quite a while, and Bitcoin was going up. As all of you remember, they used to be $200 a Bitcoin, and now they're $4,000. Shares of Bitcoin have dropped madly. It is such a drastic change, and a lot of it is affected by Trump's trade war. And this is a huge problem in global economy, because we need to find a way to balance our companies. Mm-hmm. The majority of our companies do not get steel from this country. So if we're going to do this, we can't just cut steel imports. We need to, and here's the issue too, is that companies that do send steel to us don't want to export any more steel because they have to pay too high a tariff to sell their goods here, so it's not as worth it as it used to be. And other companies here are still demanding their steel, but the steel companies that have been sending our steel to our country don't want to do it anymore because it's not worth it. It's not worth the business. If we look at Google, Google was going down, but we saw some movement here, and boom, they skyrocketed up. They kind of had a few bumps here and there, and then Google started slowing down. They started seeing difficulties. They went up, and then they kind of went up a little bit, and then boom, started seeing slow movement, went up, and then down. A little bit of movement here, up, down. And Google is on its way down right now. To be honest, it's really funny why Google's affected by this. But Google, believe it or not, has to deal with lots of new software that they have to keep installing and stay updated with browsers and YouTube and all that stuff, storage space. So that's why YouTube's affected. Now Apple's getting beat up in two ways.
Oh yeah, phones use so much of the aluminum and steel. Depends on which phone you have, but yeah.
Apple, right? So here's the issue with Apple. Of course, last time or a couple times ago, we talked about Apple's iPhone X and how iPhone X is big failure. They cut production just recently, I believe 30%. Now that is a major reason for stocks going down. We had Apple stocks were kind of, they were in a dip, and then they came back up again, and they went up, and then boom, they went down in a dip. This was after right here, that was when they cut. This was the issue with iPhone X. People didn't like it. Went up a little bit, and now we're back down here because they cut their production, and less production means less sales, less money overall. So we started seeing it go back up again. After they cut production, they started balancing out production a little bit, and then boom, we're starting to do a little bit better. Starts slowing down because people again are liking it even less. Cutting production has sent them down. They started cutting more production here. This was when we hit 30%. We were 20% right here when we went down. Now we're 30%. We started going down, right? And then right about here, boom. Trump's trade war, bam, steel, aluminum, down, Apple goes. And we start seeing it come back up, boom, boom, down. Apple keeps going. They just keep going down. Apple is not doing well right now, because they cut production, which dropped sales, and boom, trade war, Apple went down. So we're starting to see a lot of issues periodically across the market. And if we even, not just Apple, look at in general, New York Stock Exchange, NYSE, is not doing well with this.
Oh, no.
So, so we went down a little bit, right? Quite a bit. And then we went back up. We started climbing. The General Stock Exchange of New York was starting to come back up after, Apple and other companies, Bitcoin with its dropping, has affected this, right? But then we're coming back up. We're slowly making it back up there. And then, boom, right about here, we're doing okay. Just the economy is not doing so. It's not growing so much. And then, boom, trade war. And you can start to see the same general effect right about here. Tariff. Right there, tariff. Tariff has affected the entirety of the economy. Google is affected, which, it's weird, because Google is a search browser. They sell internet stuff, which is kind of weird why Google's affected. The entire economy is being so widely affected by this tariff. Everything is going down right now. So I don't know where to tell you. It might continue to go down, so I'm going to tell you, hold on to your stocks, because we know things will probably go back up again. They're going, again, the economy, life's all up and downs. That's a funny phrase that we say in economy. This is a problem. But, we'll see how our government tends to do things, and we'll see what the Fed decides to do, Fed being the Federal Reserve, and we'll see how companies do approach this. Maybe American steelworkers are going to have some changes. But it's looking kind of bad for everybody right now. So, yeah, that's that. So yeah. So that is our show. And now, you know what time it is.
It's time to spin the wheel of technicality.
Okay. So, let's see what we land on today.
And it's technicality.
Okay, so today's technicality. By technicality, energy does not create matter, it creates both forms. So by technicality, energy creates both forms. Again, do send yourself one of those send us at the JerBear email, jerrrbear333@gmail.com. Send us a video of yourself saying, hi, this is my name, this is where I'm from, and this is my win face. Hold a pose of yourself in your win face, whatever your face is when you win. And then whenever this wheel happens to land on win face, which is green right here, you will be one of the winners. So if you send yourself a video, eventually you will be getting yourself a JerBear mug. So you send a video, what's going to happen? We're going to have you at the top of the list. The first person to send us a video is going to be at the top of the list, and when it lands on WinFace, that person gets it. And if there happens to be someone else who sent a video, they are going to get it. So we'd like to feature you. What we're going to have is, instead of us saying it's time to spin the wheel of technicality,
you're going to say it.
You're going to say it. So, once the wheel lands on WinFace, you will be winning one of these mugs. So again, it goes on order of who sends it, whoever sends first. When it lands on WinFace, you're going to be one of the winners. So, hope you did enjoy this episode of Wake Up Universe. And
as always, as always, this is JerBear, and I am Sibo, and we'll be seeing you.
And, as always, if you did enjoy this video, please do comment, like, and subscribe to join the JerBear Den. And we will see you all later. Bye!